There we go. All right, so what I'm going to end up doing is my focus today is to make sure you understand how to draw Lewis structures of molecular compounds, okay? The most important information that you're going to need for today is from this page on the packet, where it's the first page where it says AP Chem Chapter 8, and then our main focus is going to be exceptions to the octet rule and general comments about the octet rule. And before I start explaining that, I want to make sure everybody understands this. Guys, this is all based on drawing Lewis structures. We've done Lewis structures. It's been several weeks. Heck, it was back in October. Thank you. Cool. So that's coming back. But basically, all you have to remember is what valence electrons are, how to do Lewis structures. So for example, since we are doing molecular compounds, our Lewis structures are going to be based on nonmetals. So just a little refresher, oxygen is a nonmetal, nitrogen is a nonmetal. If I were to draw the Lewis structures of these individual elements, you should be able to look up on a periodic table, see that oxygen is in the chalcogen group, or you can just call it group 16, and you should know that they have 6 valence electrons. So if I drew the Lewis structure of oxygen, 1, 2, 3, 4, 5, and 6. You should know how to do this. This is not anything that we have not done before. If I were to look at nitrogen, nitrogen is in group 15. If I wanted to draw the number of valence electrons using the Lewis structure, nitrogen has 5. 1, 2, 3, 4, 5. We use this information to actually draw what happens when these molecules make compounds, okay? So it is imperative that you remember how many valence electrons are found in the elements on the periodic table, specifically nonmetals. And it is imperative that you remember how to draw Lewis structures and understand how many valence electrons these elements want. 8. Don't forget the octet rule. We've talked about it. It's back again. I will discuss these exceptions in a little bit, but I have a step-by-step process. Phone call. At the worst possible moment. Schooler. Okay, thanks. Okay, luckily I have a step-by-step process to show you how to draw these molecules. I'm going to do several examples for you, and then we'll practice them at the end. So take that page and turn to the next. Ignore the warm-up. Ignore the warm-up. Ignore this page. We are going to get to this. We'll talk about geometry. There we go. You want to find the page, and I would star this page. And I would make sure you know specifically where this page is at all times. These are the rules/steps for writing Lewis dot structures for covalent compounds. So what we will be doing is we will be using this page and the page that has the exceptions to the octet rule. So you're going to be wanting to flip back and forth when I reference it. I'm going to read through the instructions, and then, guys, the best way to do this is to learn how to do it, okay? Wow, that absolutely was a weird statement. The best way to do it is practicing how to do it. So what we are going to end up doing is when we want to draw a molecular structure, we need to know the number of valence electrons. We will need to use an electron negativity chart because the least electronegative is in the center. Remember that chart that I showed you on the screen a little bit ago? That's the electron negativity chart. You should know what electron negativity is. We talked about it in periodicity. Okay? We are going to remember that each element wants 8 valence electrons. There are a couple exceptions, though. Hydrogen is the most common one. Remember, hydrogen only needs 2 valence electrons. Okay? And then what we will do is we will figure out, hey, do we have enough valence electrons to make a full octet? I need to see you after class.
Yeah.
Just put it right there. Not that. There you go. My bad. Okay? And then we'll kind of go through all these steps and discuss, because some of these steps won't apply to us today. All right. So the best way to do this is to just try it out. So I would go ahead and I would find a spot either on this packet or, and you could honestly, where is it? You could honestly use this warm-up page. See how it's all blank? You could use that, or you could use a separate sheet, because I'm going to show you how to do these examples. Up to you. The first example that we're going to do, and can they see me on the screen? Yeah, kind of. Is we are going to draw the molecular structure of sulfur dioxide, SO2. You don't know how to name it yet. It's real simple. That'll take a day, so I'm not going to worry about it today with a short class. So what I'm going to do is I'm going to follow those instructions. And then, guys, I want you to be very well aware. There are exceptions to the octet rule. Okay? So when I go through this, understand that I will tell you how to find out if those exceptions are hit on a particular element. Okay. So step one is to count the number of valence electrons that you have in your compound. Sulfur, right below oxygen on the periodic table, that's group 16. That entire group has 6 valence electrons. So we have 6. How many oxygens do we have? 2. Okay? So that means each of those are going to have 6 valence electrons apiece. Oh, joy, 666. Perfect way to describe this. So, if you count all those up, that means we have a grand total of 18 valence electrons that we are going to be using. What that means is when you draw this structure, you better have 18 total dots. Okay? That's going to be important that you always do this step. All right. Now, step 2 says to place the least electron negative element in the center. That's where you would use this chart here. Okay? If you remember, guys, electron negativity is the desire or ability to bring in electrons. Now, you don't have to flip to it. I'm going to tell you what the least electron negative is. But, guys, that category is right there. There's a lot of information, but this chart is mainly just for that one column that says electron negativity. The least electron negative will go in the center. And in this case, if you were to look it up, it is actually going to be sulfur. So that means, guys, is when you're drawing these, you have to think there should be at least one central atom. Sometimes there's more. We're not going to do any more than one today. So when you draw this out, and I would strongly recommend that you start doing these in pencil. I'm drawing this extra big so they can see it on the phone. Yeah, they can kind of see it. Okay? When you have your central atom, place everything else on a flat plane around it. What I mean, guys, is we assume that there's a flat plane here. Assume this is just like a Lewis structure. Side, 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 side. Remember how when we draw dots, we put 2 up here, 2 up here, 2 up here, 2 up here. You know when we draw Lewis structures, each side gets 2. Okay, when you make a molecular structure, okay, we start on either of these sides, then we can start to fill it in. But what I'm saying is don't fill in these corner spots until we get used to doing this. Will we eventually? Yes. But I'm trying to keep it simple today. So what that means is I'm going to surround it by oxygens. Now you might be asking, Mr. Schooler, why don't you just put an oxygen here and an oxygen here? Anybody remember what's the charge in an electron? Oh, come on, wake up. Yeah, Ethan.
Positive. Negative.
There we go. It's negative. Remember, and this would honestly work if they were positive. It would be the same idea. They are negative. Okay, remember, if you have the same charges, what do they do to each other? They repel, right? So if you were to put something with electrons here, you can't put with something with electrons here because it'll push it away. So essentially just think, hey, they're going to spread out as far as they possibly can. This gets easier and you'll just know it by secondhand by the time we do it. But I'm telling you now, start it on this plane. Okay. So right now I have 18 valence electrons, and the next step says give each atom 8 electrons. We don't have hydrogen, and we'll see what happens. Okay, so I'm going to give each of these 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And yes, I know it looks kind of funky. If you're doing this with a pen, I'm sorry. Guys, once you get good at this, you're not going to have to do this step because this is just extra time. So we have 18 valence electrons that we can use. And if we look at all the ones after we've given it a full octet, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That ain't going to work out. But what it does tell us is it can tell us we can start eliminating valence electrons. Does it matter where you eliminate them from? Absolutely not. Okay? But you have to understand you can only have a maximum of 18. So what I would recommend, and guys, this is perfectly however you want to do this, what I would recommend is you start eliminating the extras that are in between, and here's why. Okay? Any electrons that are between two atoms are shared, meaning both of those elements share all 4 of these. Not these, but any of them that are in between. So if we're looking at sulfur, if they're sharing all of these, sulfur is sharing 2, 4, 6, 8, 10, 12. Oh my gosh, we don't need that many. Makes it a lot easier. Well, let's just go ahead and take away those 2. What's that put us down to? 20? Yeah, puts us down to 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 2 extras. Take them from anywhere. Doesn't matter. Okay? I'm just going to go ahead and I'm going to take them from here. 18. Mr. Schooler, is this right? Here's how you can tell if your drawing is correct so far. Octet rule. Do they have a full octet? 2, 4, 6, 8. Well, this oxygen does. 2, 4, 6, 8. Well, that oxygen does. 2, 4, 6. If your element does not have a full octet, what you have to do is you have to start moving valence electrons to share with that element. Okay? Now, when you start to do this, one thing I want to push across to you guys. It does not matter where you pull the electrons from. What I mean is that electrons are not always shared equally. Meaning, oxygen isn't going to give away just 1, and so is sulfur, meaning they're not going to each give away 1. Sometimes oxygen will give away all of them to share. It does not matter where you pull those valence electrons from, okay? All right. So I got to share some with sulfur. All right, well, when you do this, if I take this here, you get that drawn. Okay? But here's the problem. Let's see if I can follow it. Where is it? Where's my exceptions to the rules? There we go. Okay. When you look at this, right now it looks like your SO2 is absolutely correct. But this is why you should always look at the octet rule exceptions. Because right now, this oxygen's sharing 2, this oxygen's sharing 4. And look right here. Some atoms exceed the octet rule. some atoms have the ability to go above and beyond 8 valence electrons. And it says in the exceptions to the octet rule where to look at. It says some elements exceed the octet rule. This is seen only for the elements in period 3 and beyond. Remember, periods are horizontal? Look where sulfur is. Helium and hydrogen are period 1. Lithium, beryllium, boron, etc., are period 2. Sulfur is in period 3. Sulfur is going to exceed the octet rule. And you might be saying, well, Mr. Schooler, why? Oxygen loves to have double bonds. This one does have a double bond, and I'll explain how we know it's a double bond, but this one doesn't. Every 2 electrons that are shared is a single bond. So if oxygen over here is sharing 4 electrons, 2 represents a bond, this is a double bond over here. You can have single, you can have double, you can even have triple bonds. Oxygen loves to have double bonds, and it likes to keep it even on both sides. So if this one has a double bond, we want to make sure this one has a double bond. Can we do it? Absolutely. Why? Because of this exception. Period 3 loves to have more than 8 valence electrons because it can. So we're going to take that, put it in the very center here. A double bond, I know this because 2 electrons that are being shared is a bond. If there's 4 of them, that's a double. So when you have 2 electrons being shared, you draw a line. This represents that you have a bond. This represents you have a bond. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 valence electrons. Sulfur has 10 valence electrons that it is sharing. Can it do it? Absolutely it can. Oxygens, 2, 4, 6, 8. That one's good. This oxygen, 2, 4, 6, 8. That one's good. All of the rules are satisfied. This one has been completed. This is the drawing of the molecular structure of sulfur dioxide. Now, here's some good news. This is one of the harder ones, okay? They're not always having to be this thought out, because we're going to do some easier ones next, okay? So don't panic. This will become second nature to you down the line. It just takes practice. Okay, so sulfur dioxide. My point that I'm trying to get across is make sure you always look and figure out, are any of my exceptions being met? All right, let's do another one. Let's do nitrogen trihydride. My marker's already gone, really? NH3. All right, we're still good there. NH3. Now notice this one has hydrogen. Remember, hydrogen can only hold a maximum of 2 valence electrons. Keep that in mind. All right, so the first thing we need to do is we need to find out how many valence electrons do we have. Nitrogen has 5. Hydrogen, there are 3 hydrogens. Look where hydrogen is. Group 1. How many does group 1 have? 1 valence. There are 3 of them, so 5 plus 1, plus 1, plus 1. 8. We can have a total of 8 dots in our drawing. Now, regardless of electron negativities, hydrogen cannot be a central atom. Cannot. I do not care. Engrave that into your brain. No matter what, hydrogen cannot be central. But nitrogen can. So therefore, by rule of exception, because hydrogen cannot be central, nitrogen will be. So nitrogen is going to be our centralmost atom. Now remember what I told you guys the last time about drawing? Where do you put these hydrogens at? We start, well, we put an oxygen over here, then an oxygen over here. Well, we got 3 hydrogens. But remember, we're looking to put, just like valence electrons, just put them on the sides. I'm going to put a hydrogen here. I'm going to put a hydrogen here. And then put it one other spot. Doesn't matter. But notice I am placing the shape based on valence electron drawing or Lewis structures. Remember, there's like an imaginary square here. You can put an element on each side. Okay, so I'm going to go ahead and I'm going to give all of them a full octet. I'm going to start with nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. How many valence electrons can hydrogen hold? You can just say it. 2, right? Full octet. Full octet. Full octet. Nitrogen, 2, 4, 6, 8. Full octet. We can have a total of 8 valence electrons. 2, 4, 6, 8. We're done. This one just works out. A lot of these are that simple. So basically, this is why I tell you to do those steps, because if you give the full octet and you notice, ooh, hydrogen can't have any more, that means we've got a bond here, we've got a bond here, we have the bond here, and that one's just a lone pair. This is referred to as a lone pair. Bonded pair, lone pair. Bonded pair, lone pair. That'll become important later on. Can that still be seen? Yeah, I think we can still see it. And that's all there is to that one. Let's do another one. Any questions so far? I'm sorry, I'm getting a little ahead of myself. I'm sure there's a lot going through your minds right now. I don't expect you to be like, ooh, I got this. But yeah, Ethan.
If we don't put that line there, we keep it as 2 dots. Well, like, that'd be kind of.
Where are you looking at? Here?
Yeah.
You have to make the line. Yep. Now, it can be like this. And you just connect it. Like, you don't have to redraw it. That's fine too. But you do have to make a line because a line represents a bonded pair being shared. Represents 2. Any other questions? On to the next one. All right. Let's do H2O. Here's another one. You guys should be able to immediately look at this formula and know which one's going to be central without even looking at your electron negativity chart. Oxygen will be. Hydrogen can't be central. So we have 2 hydrogens, we have 1 oxygen. So 1 electron, 1 valence electron plus 1 valence electron plus 6. We're going to have 8. All right, H2O. So oxygen's going to be central. We're going to have a hydrogen and another hydrogen. Okay. Now remember, I can only use 8. But if you give them a full octet, hydrogen's got a full octet. This hydrogen's got a full octet. How many more does oxygen need? Needs 4 more. 1, 2, 3, 4. 2, 4, 6, 8. Oxygen's good. Hydrogen's good. Hydrogen's good. 8 total valence electrons. 8 are drawn. Draw your lines. Done. Again, these are a lot of single bonds on here. Now, I'm not going to require this yet, but I want to give you a heads up. Starting next week, okay, because this is going to be what you guys draw. Starting next week, there will be one extra step for this because technically, and I'm not going to have you draw it right now. Technically, water looks like that. And the reason for this, and again, I'm just giving you a little preview. I'm not going to expect you to have it this week. Due to the strength of sharing versus non-sharing, the non-sharing or the lone pairs prefer to be closer together, and the bonded pair prefer to be closer together. So next week, I will be starting to implement that. I'm not worried about it. You can leave that like that today. Okay, but I'm just giving you a heads up. Do another one. Just trying to give you examples, people. Let's do carbon monoxide. What if we just have this? C and O. Well, obviously there's not really a central atom, although it would be carbon if we were. Carbon, group 14, 4 valence electrons plus 6. We have 10 valence electrons. Okay. I lost my train of thought. Okay, here we go. We have carbon and we have oxygen. We don't really have a central atom in this case. I'm going to go ahead and give them a full octet. 2, 4, 6, 8. Carbon's got a full octet. Oxygen's got a full octet. 2, 4, 6, 8, 10, 12, 14, 16. Way too many valence electrons. We can only have 10, so that means I got to get rid of 6. I'm just going to get rid of them. 2, 4, 6. Okay. So now I have 2, 4, 6, 8, 10. I have to move them. And guys, again, I want to remind you, it does not matter where the electrons come from. They can come from carbon, they can come from oxygen. Distribute them so that the octet rule is made. Because these follow the octet rule, there are really no exceptions to that. All right, well, I have these two already being shared. So carbon right now has 4 valence electrons. Oxygen right now has 10, way too many. So I'm going to take away 1 pair of those, and I'm going to give it to carbon. 2, 4, 6. Okay. This oxygen has 2, 4, 6, 8. Because if I take 1 more and put it over at carbon, then I still have the same problem. 2, 4, 6 for oxygen now. 2, 4, 6, 8. So when I keep on moving them back and forth, I can't get them to even out. So where should you put them so that they both can have them? Go ahead, Ethan.
Make a double bond.
Well, there's already a double on because I have these two, but I know what you're going to say. Like, basically all I'm asking is where should I put these electrons so that they can be shared? Muhammad?
In the middle?
Yeah, put them in the middle. That's what you were trying to say. It's just there's already a double bond. So what we're going to do is, if I keep moving electrons back and forth and I cannot satisfy the octet rule, put them in the center. Do that. 2, 4, 6, 8 for carbon. 2, 4, 6, 8 for oxygen. And clean up your drawing, by the way. That would become a triple bond. And guys, the reason I move the other dots is the electrons like to spread out from each other. Okay, real quick. Your assignment is on the very last page of that whole entire packet. Your assignment, you see where it says Lewis structure practice, single bonds, double bonds. On the other side it says triple bonds, and then you choose. These are the ones that you need to do. Oh, I just did that one. Boo. Okay. Go ahead and do 1, 2, 3. Should be easy. Six and 9. 1, 2, 6, 9. 10. Is that a negative sign? Yep. And 12. Excuse me. And 12. Guys, it will be a completion grade, so just have them done. All right? Bring those tomorrow. I'm going to say goodbye to my online people.